Examination 2016, No Way Back Part 2. This is the second video based on the data sheet, and it refers to pages 5 and 6. The first thing you're being asked to do is explain why the acceleration due to gravity of a spaceship leaving the Earth is given by this equation. So first of all, if we have a look on page 5, then towards the top you'll see the relevant information is here, where it's talking about the only force acting on the spaceship after leaving the Earth is due to gravity. So what we're assuming here is that the rocket is actually fired, it's used up all its fuel in order to accelerate away, and now the engine has cut out, and so it's only gravity that's actually acting on the spaceship, and the spaceship has to be going fast enough so the gravity cannot pull it back down to Earth again. So if we have a look at it, the key equation that we're trying to show is here, a equals minus g me over r squared, and the other key bit of information is that the acceleration of the spaceship is acting vertically downwards. So our general rule, which we've been using throughout, is that the gravitational force is g m over r squared, where capital M is for the larger object, little m for the smaller object, and r is the distance between them. G is the gravitational constant. And we're saying now that that is equal, in this case, to gmem over r squared downwards. And so all I'm doing is I'm saying the larger object is the Earth, the little object is the spaceship. Now, before we use F equals ma on this, we need to take account of direction. And so if we look, you'll see the acceleration is going up, but the force is pulling down. Now that is why we get a minus sign here, because the acceleration, we're looking at the rate of change of a velocity, and the velocity was going up, the force is pulling in the opposite direction, so we have to say ma is minus this force, because the force is pulling the opposite direction. And then all we need to do is to cancel things down. And so if I look at this, I can cancel out the m's, and I get that the acceleration is indeed minus g me over r squared, which is what we wanted to show. Next bit. You're given that v dv dr is minus g me over r squared, and from that you've got to work out the escape velocity, which is v with a little e to show its escape velocity, is this square root over here. So again, let's look at the relevant bits on the data sheet. This is further down on page 5, and you'll see that there's lots of important information here. So if I actually look at some of those, and let's change it there. These are the key bits of information. So our escape velocity is VE, RE is the radius of the Earth, and we're assuming that the velocity v is 0 at some distance away from the Earth. So basically, the spaceship might be driving off very fast, but eventually it's going to reach a position where it stops altogether, and that's going to be when you've got to a distance r away from the Earth. And then it's saying that we can show these things here, and we will gradually work out each of these statements from it. So the first one, we are told that v dv dr is minus g me over r squared. That's our starting point. Now, this is a differential equation, and so we are solving it by keeping the dv with a v, but the dr over here needs to move across. So effectively you're multiplying by dr. And then you've got your v dv here, you've got this statement, the minus g me over r squared stays over here, but the dr is now moved across for it. And then we put in two integral signs. And that's the standard way to solve a differential equation by variable separable, is that we have the v bits with the dv, the r bits with the dr. Now, often what you will have done when you solve these is you will have solved them and had a plus c and then worked out c. But another way of doing this is to put in limits right from the start, just the same as you normally have limits for integrals. But we've got to make sure the limits are the right way round. So at the start, the spaceship starts off on the Earth. So its distance from the centre of the Earth is RE. RE, the radius of the Earth. At that time, it's just fired its engines and it goes up to the what we hope is the escape velocity VE. And then later on, when it eventually gets to a point where it's capital R away from the centre of the Earth, its velocity has gone down to 0. So we're keeping the things consistent. So when we're on the Earth, so we're at the radius of the Earth or just above the Earth, then we're at our escape velocity, and when you get to R, the speed's gone down, the velocity's gone down to 0. So we've got this integral to do here, and also this one to do here. Now to integrate this one, you'll see the r squared is underneath. So we're going to have to use negative indices. We use the fact that 1 over r squared is the same as r to the minus 2. So 1 over r squared is r to the minus 2. So you'll see the rest of it stayed the same. The limits are the same. I've got my minus. I've put my GME in brackets. It doesn't have to be in brackets, but it's just to show that that is that part, and then my r to minus 2 after it. Okay, and GME is a constant. G times ME. G is a constant. Mass of the Earth is a constant. The r to minus 2, that's what's varying. So now let's do our integrations. Well, if we integrate v dv, it's the same as integrating x dx. So I increase the index, which was 1. That goes up to v squared. And then I divide by the new power. So it goes to v squared divided by 2. And those are my limits. I write them down here. So I've done my integration. Now let's integrate this one here. Same idea. This part is all constant. That will stay the same for minus GME. But this, I increase the power by 1. Well, minus 2, when I increase it by 1, goes up to minus 1. But then I have to divide by the new power, so I divide by minus 1. So you see I've got the minus GME as before. But r to the minus 2 goes to r to minus 1 because I increase minus 2 to minus 1, divide by the new power, divide by minus 1. Here are my limits, r and re. Now, first stage, I can simplify this because dividing by minus 1 just changes the sign. It was a minus sign, so it just changes it to a plus. So those cancel out, and I'm left with GME r to the minus 1. And then, to make it a little bit easier to understand, just like r to the minus 2 was dividing by r squared, r to the minus 1 is dividing by r. So I get GME over r, there's our limits. Next stage is to slot the limits in. So here, when I put in 0, I get 0 squared divided by 2, which is 0. When I slot in VE, I will get VE squared over 2. So 0 squared divided by 2, 0, and then I take away when I'm using the other limit, so I take away VE squared over 2, because it's always put in this limit, and then take away when we put in that limit. Now let's do the same thing here for this one. So I first of all am going to replace the little r by capital R, and then I'm going to take away when I replace it by RE. So I get GME over capital R, take away GME over RE, the radius of the Earth. Now, the easiest way to handle this is again to deal with the signs first. If you look at this, 0 minus VE squared over 2 becomes minus VE squared over 2. Well, I'd sooner have that as plus, so I'm going to multiply this side by minus 1 to turn it into VE squared over 2. If I do that, I've also got to multiply over here by minus 1. And that means that that bit becomes minus, because it was plus, and this bit that was minus becomes plus. So it's like swapping these round. When I multiply by minus 1, that becomes minus, that part becomes plus. Next stage. Let's look at what happens as this r becomes very, very big. This is the distance of the rocket away from the center of the Earth. And what we've put here is as r tends to infinity. That's what they put here on it. It means as the r becomes very big. Well, we're dividing by r. Now, it doesn't matter what this number is here. If you divide by something which keeps getting bigger and bigger and bigger, eventually you'll get to the stage where all of this part will disappear. So you can take a big number, you can have something which is in the millions, but if we divide it by something which is in the billions and then in the trillions, where you're dividing by something that's getting bigger and bigger, eventually this part will disappear, it will go to zero. And so we can say that GME over the capital R, as R becomes bigger and bigger, this gets smaller and smaller, eventually disappears. And that leaves us with VE squared over 2 is equal to GME over RE. And then all we have to do is multiply by 2. So I get VE squared is 2GME over RE. And then, because that's VE squared, square root both sides to give me VE is the square root of 2GME over RE. And we've proved the result that we had at the top. That's quite complicated. If I were you, I'd go through it slowly, carefully, pausing the video as necessary to make sure you understand it. Let's go on to the next stage. Show that the escape velocity for Earth is approximately 250,000 miles, 25,000 miles per hour, 25,000 miles per hour. I think this is at the top of page 6. Okay, so let's have a look. We're given a lot of information again here, if the Earth is assumed to be a sphere and so on. So again, let's look at that lot and let's make it so that it's easier to see the key bits of information. We're told the radius of the Earth, that's an RE, I know it's a little bit hidden by my orange outline. This is the mass of the Earth, and it's saying we can calculate the escape velocity as 11,200 meters per second, which we'll then see what that is in miles per hour. From the previous page, we found out, I know I've rubbed it off now, that that's what VE was, the square root of 2GME over RE. So we start with that position. Let's now put in the information you've got, but you'll also need to know the constant capital G, what that is, and that's earlier in the data sheet. We're told it's 6.67 times 10 to the minus 11. So let's start with this part without the square root. We'll put the square root on at the end. So it's going to be 2 times our G value times our mass of the Earth, and then we've got to divide by the radius of the Earth. So all I've done is I've slotted the numbers in. I always prefer to simplify these things a little bit first. You can put it straight into the calculator, but with the indices, it actually will save you time if you can do the bits to do with the 10 to the powers of, if we can simplify those first. So where we're multiplying, you're going to add the indices, and where you're dividing, you'll subtract it. So what we're going to get is this. That stays as 2, that stays as 6.67, that stays as 5.98, multiplied together, still 6.378 on the bottom, but if we look at the powers of 10, then where you're multiplying, you're doing minus 11, add 24, that comes to 13, then divide means I subtract the 6, so I get 10 to the power of 7. And then if I work that out on my calculator, it comes to 1.25 times 10 to the power of 8. That's in standard form. So VE is the square root of this. So all I have to do is square root that, which comes to 1.12 times 10 to the power of 4. Then, next part. This is in meters per second. You'll see that we're dealing at the moment, it's the standard SI units, kilograms and meters and so on. So we want to be dealing with it and saying, well, let's get rid of the standard form first of all. So I'm multiplying by 10 to the 4. If I multiply by 10 to the 4, it's like moving decimal point 4 times, or moving the numbers across 4 times, and I get 112, and then 2 more noughts. So it's 11,200 meters per second. Let's turn it into kilometers per second. Well, there are 1,000 meters in a kilometer, so I divide by 1,000, and I will get 11.2 kilometers every second. So it's quite fast. Kilometers per hour. Well, there were 60 seconds in a minute, 60 minutes in an hour. So in an hour, I'm going to go 60 times 60, 3,600 times as far. So I'll go 3,600 times as far. So 11.2 times 3,600 comes to 4320. So I've got my 3,600. I'll just multiply that by 11.2. Let's check it. 40320. Now that's kilometers per hour. And then finally, into miles per hour. Well, there's 1 mile, it's 1.6 kilometers. So what I'm going to do there is to turn it into miles per hour, divide it by 1.6. So this is an approximate value, but we only want approximately miles per hour. So divide it by 1.6, and it comes to 25,200. So it is about 25,000 miles per hour. Okay. Next one. Show that the escape velocity for Mars is approximately 45%, just under half the escape velocity from Earth. Okay, well, what I'm going to do here is I'm going to work in meters per second, so I don't have to turn it to miles per hour. So the escape velocity from Earth we found was 11,200 meters per second. Let's have a look at it now from Mars. So again, that's the key part. They're saying it's the very last paragraph. Let's see if there's any really useful information on it. Okay, and there it is. We're told that Mars, the radius of Mars, we're told the mass of Mars, and we're told the escape velocity, what it should be, about 5,000 meters per second, and that's about 45% of that for Earth. So let's see what happens. Well, on Earth, the escape velocity from Earth was square root of 2g mass of the Earth divided by radius of the Earth. So if I do the escape velocity for Mars, I put Mars rather than just m, because we were talking about the moon in the last video. I don't want m to count for both of them. So the escape velocity for Mars is 2g times the mass of Mars divided by the radius of Mars, but again, square root it all. So slot the numbers in, and we get 2 times g, well that's the g value from over here, 6.67 times 10 to the minus 11, 6.67 times 10 to the minus 11, then we've got the mass of Mars there, then the radius of Mars there. Like before, I'm going to simplify it first. You don't have to do this, you can all go on the calculator, but I'll put 2 times 6.67 times 6.4 on the top line, 3.397 on the bottom, and now dealing with the 10 to the power, and minus 11 add 23, that comes to 12, and then I'm dividing by here, so I take away 6, so I get 10 to the power 6. Work that out on my calculator. I won't bother pressing the buttons, you can do it yourself. It comes to 2.513 times 10 to the 7, and that is something we need to then square root. That is VE, I put VE, I should have been, V Mars, I'm doing the right thing. That's the velocity of Mars squared, that I've just worked out. So the escape velocity for Mars, I need to square root that, and that comes to 5.01 times 10 cubed, or 5,010. And 5,010, that's not very far away from 5,000 meters per second. So turn it in, now compare it with Earth. We looked at Earth, we found 11,200 meters per second. So on Mars, we've got to compare 5,010, we want that as a percentage of 11,200. Well, 5,010 divided by 11,200, I will do that, 5010, divide it by 11,200 equals about 0.447, turns into a percentage, means I multiply by 100, and that comes to about 44.7, 45% of the escape velocity for Earth. So we've shown that it does work. Okay, final question. What happens if a rocket doesn't reach escape velocity? Answer is here. Okay, good luck.